thanks. It's a pleasure to be virtually here, I would say. Thanks for the invitation. This is, of course, a topic I'm always happy to talk about since it's pretty much at the core of our work. So indeed, I'll be talking about machine learning potentials for modeling radiation damage. But before I do that, I'll give a fairly long introduction since I'm not sure what the exact background of the listeners are. So it's good to put things in context. And this is work done by many people in our group, but I just put the three most active senior scientists here, myself, Professor Flora Joan-Peikkova, and President Fredrik Granberg as co-authors of this presentation. But before I go on, I'd like to send greetings also from the fabulous white nights in Helsinki around midsummer. This here is a picture taken at 11 o'clock at night, just a few days ago, and a few hundred meters from where I live in Helsinki. So you can see that even at midnight, it doesn't get fully dark, and it's a really wonderful time to be here. And right now, it's actually also exceptionally hot. It's plus 32 degrees C where I am now, which is quite exceptional for the Finnish summer. But going towards the science, so we work at the Accelerator Laboratory in Helsinki, which has about 50 scientists working on both experiments and computer simulations related to radiation effects. And we have a number of mid-size accelerators. The largest is a 10 megawatt tandem. And then we have a number of implanters, nanocluster and equipment, and so on, and positron annihilation equipment. So we are quite versatile in the ion and positron accelerator field. And then for materials synthesis by other means and manufacturing, we are collaborating with the rest of our physics and chemistry departments. And in total, in the simulation side, we are indeed 4 senior scientists in total. Also Antti Kuronen is a 4th one, and then a number of younger scientists. Actually, this graph, to be honest, is a bit old because due to the corona, we don't have pictures of all the new people, but the number of people is about right, but several people in this picture have actually left the group by now. But indeed, we have more than 580 publications actually by now, and 41 PhD theses, and are closely working with many of the leading accelerator and fusion labs in the world. So coming to my talk, so I'll give a little bit of introduction into the radiation damage and motivation why it's important, and a very brief introduction into the basic physics. Although from Mosab's introduction, I understand that you may know that. But then I go towards the actual new part of the talk. So I first talk about the molecular dynamics method in case you are not aware of it, but then about interatomic potentials and how that leads into why we want to do modern machine learning potentials. And then our key contribution is here that we took one of the most used machine learning approaches, the gap approach, and made it suitable for radiation damage calculation, because the basic gap was completely unsuitable for it, and I'll show you later why. And then I'll give some results on this both for metals and for semiconductors. So when we talk about radiation damage in metals, usually it's bad. I mean that is an undesirable effect. That is when you irradiate metals, they tend to become elastically harder, which you might think is good, but the problem is then that they also become more brittle. And this becoming more brittle is certainly not good. The other thing is that they also tend to swell. And this is a classical picture of 2 rods, one control rod and one rod which have been for a very long time in a nuclear reactor. And you see this is a regular stainless steel, and you see that it has swollen a huge amount. And of course, when engineers building equipment, typically their tolerances of the order of 0.1% or less in terms of the dimension. So you can immediately tell that you can't have you don't want something like this to happen to a structural component. I mean, the whole structure would break, which of course in a nuclear reactor is unacceptable. So because of this, it's important to know and understand the radiation effects in metals, which are used in nuclear reactors. be able to select metals which withstand it well enough, or use conditions like temperature, maybe even electromagnetic field under which the metal tolerates the conditions. But then the other side of radiation effect is the positive one. So when people make semiconductor chips, and this includes all modern chips which are in your mobile phone and laptop and whatever electronic device you are using in the last 20 years or so, they have all been using ion implantation in the manufacturing of the chip. So a modern chip, they have at least 15 ion implantation steps. So it's one of the many, of course, it's not the only process, but it's one of the many important processing steps which are used to make modern computer chips. And this is a big industry. The entire chip industry is, of course, hundreds of billions of dollars worldwide by year. And this implanter part of it has been estimated to be several $1 billion just making the implanter equipment, and also then, of course, maintaining and upgrading it. So because of this, it's also important to understand radiation damage in silicon and other semiconductor chip materials to be able to develop better and more accurate and better process control, and then better computers. So going towards the physics of it, so when we have an IO, what is the question I try to answer here on this slide is, what is the origin of a radiation effect producing damage in solids? And now I'm not talking at all about photons, gamma rays, electrons, because most of the time in solids people are interested in either ion or neutron damage. We have worked on both photon and electron damage as well, but for the sake of time, I won't mention that. But yeah, so if you have an ion accelerator like what we have at our lab, you have ions coming in with a well-defined energy. Often the energy spread is so small that you can say that they are monoenergetic. And then they will hit a material and modify it in one way or other. Plasmas can also, if it's a high voltage plasma, they can also have essentially be cause ion implantation, especially if you form a sheet potential. Then the ions, positive ions escaping from the plasma, will be accelerated over the sheet potential and hit the material. Neutrons, then the picture is different. Neutrons in a nuclear reactor, they can travel very deep, tens of centimeters easily in typical materials, sometimes even meters. And most of the time, because they are not electrically charged, the neutrons travel in a straight path, but with a small probability, if they come close enough to the nucleus, they will have a nuclear collision with the nucleus itself and give the nuclear recoil energy. Most of the time this is elastic, so there is no nuclear reaction, it's just a hard sphere collision, and then they transfer energy, which can be calculated from a fairly simple two-body kinematics. So the upshot is that for typical mega electrovolt neutrons used in nuclear reactors, the recoil energies are of the order of 10 to 100 keV. And after you have started a recoil, it produces damage fairly similar to an ion producing damage coming from an accelerator if the energy is the same. The difference is, of course, that when you have an ion, you have the surface nearby. When you have a neutron, it's very, very unlikely that there would be a surface or interface close by. So when an ion comes in, or if this is a neutron, you can imagine there is no surface, but then you would have a recoil here. What happens is that at the high energies, because of the collision cross sections, there are mainly the collisions with electrons, electronic stopping power. But then when the ion has slowed down enough, the collisions with nuclei, the cross section becomes larger, and you get the nuclear stopping power, which means a big set of atomic collisions. And now the rest of the talk is basically about how we model these atomic collisions, because that's what then modifies the material in a good or bad way. And here to just give you a flavor what it may look like. These are both simple examples done actually for illustration purposes, but they are still relevant also to the research. So this is one of the simplest possible cases. This is a 1 kV xenon ion impacting on copper. So here is the xenon ion, here is the copper, and the color scale is the kinetic energy of the atoms. So initially they are at the copper atoms are at room temperature, so the kinetic energy is quite low, so they look blue, and the 1 kV is above this top of this energy scale, so it's red. Now, when you start the ion, you see that it comes in, it collides with the atoms, and you get what's known as a collision cascade. But because there is a surface, some atoms can fly off, and you get sputtering of the surface. And then if you look at this inside the material, this is now a slightly different energy, but similar, or what an illustration, a typical case, this is a 10 kV gold self-recoiling gold, and now there is no surface. So what I'm plotting here is a 2-dimensional cross-section of a 3-dimensional simulation cell. And here, this one here is the high energy atom. Now the color scale is a bit different, but blue is still cold and red is hot. White is the hottest in this one. So now you have again a set of collisions. Hot region is formed, but then eventually this one cools down. This collision cascade stuff is pretty much recrystallized. Actually, in the end, you see that there is almost no damages left, just a few vacancies in this particular cross section. There is a small interstitial feature there. This fact that in metals almost all the damage in the bulk regenerates is actually very good. Otherwise, nuclear reactors couldn't be used at all because the radiation tolerance would be something like 2 orders of magnitude lower than it is. So it's actually very important that there is this recrystallization effect. And we have studied a lot the reasons to this recrystallization effect, but make a long story short, basically just the fact that you are close packed atoms in a close packed atoms. It's really difficult to find any other place except close packed positions. So the metal is able to recrystallize almost perfectly. So, okay, so that was to give you a flavor. But now, if you look at this, again, how to do those molecular dynamic simulations. And for radiation effects, it's not so simple. I mean, you can't take if you take a textbook on molecular dynamics, regular textbook, which doesn't concern with radiation effects, and use the algorithms there for radiation effects, you will go horribly wrong. So don't do that. Well, the good news is that modern codes like LAMPS actually have all the features needed to do radiation effects. They're just not on by default, so you have to know how to switch on these features to do MD correctly. But if you look at the physics sides, what happens is that first you have the high energy collisions between nuclei, and this stage is not a thermodynamic stage at all. Thermodynamics doesn't apply because it's essentially like billiard-ball collisions. The time between collisions is of the order of a few femtoseconds, which is way shorter than the thermodynamic relaxation time, which is order of 1 picosecond. So it's really not a thermodynamic system because there isn't time for equilibration. Same time as this one, you have the energy loss to electronic stopping going on. But then after a while, the ions cool down, as you saw in those animations. And then when the kinetic energy of the ion is of the order of magnitude of 1 eV, you have a transition where thermodynamics starts to apply. And then at that stage, you need realistic equilibrium interaction models to simulate the atoms in equilibrium. And then you would ideally need want to have an interatomic interaction model, which is good enough to simulate all materials processes, phase changes, segregation, sputtering, defect production, because all of this is experimentally known to happen during ion irradiation. And finally, after the primary damage state, here basically stages 1 to 5 is the primary damage state. But then after that, if you have produced any defects, they can start diffuse. If you have made a crater on a surface, it can start by adatom migration, filling in the hole and so on. And this stage is post-primary damage. This can go on from basically 10 picoseconds when the primary damage state ends up to years. It can go on, well, up to the lifetime of the universe in principle. So this can go on forever. So this is, and I emphasize that regular molecular dynamics only deals with stages 4 and 5. So that's why you can't use a standard molecular dynamics to model this. Well, but the good news is that if you know how to do your molecular dynamics right, you can do everything else except this long-term effect with molecular dynamics. Nowadays, with accelerator molecular dynamics, one can also, to some extent, do this long-term relaxation of defects. But again, for the sake of time, I mean, today I'm going to talk about that. The first stages can also be done by binary collision approximation simulations. That's an older method than molecular dynamics, which historically has been used a lot, but nowadays, when people are more concerned about the materials modification, many people have switched to molecular dynamics, which really allows also to look at the materials modification in much better detail than binary collision approximation. So what is this molecular dynamics? Well, this I'll give you a short introduction in case you're not familiar with it. One could, of course, give a whole course about it, and we actually do have a whole course about molecular dynamics online if you're interested. But basically, you start giving atoms initial positions of velocity, choose a short time step. Then this is the crucial physics stage. You get the forces acting between the atoms, and this can be done either classically by having an analytical potential function, taking its derivative, or quantum mechanically, or you can use machine learning, which in a way is in between. But ultimately, machine learning is still an analytic. Well, it's a iterative, sort of an iterative numeric analytical method, or numerical analytical method. So it's still in this category. But at best, it can have the quantum mechanical accuracy, and that's why it's in a way between these. Well, once you have the forces, the rest is then numerical mathematics. You get the accelerations with Newton's law. That's trivial. But then you move the atoms, and here the numerical. This is solving different differential equations numerically. So this is a numerical mathematics thing. These three terms for the positions and 2 terms for the velocities are already enough, but in practice, one wants to add a couple of correction terms to make it numerically more accurate. Then you move the time forward, and then you repeat. Okay, this is, as I said, the simpler version. There is like, if you apply pressure and temperature control and so on, there is many intermediate stages. Of course, you want to output stuff, but this is just to give you the basic idea. So, but as I emphasized in this molecular dynamics, everything else is basically known how to do arbitrarily accurately from numerical mathematics, except the forces between the atoms. And this is, of course, a very fundamental question in materials physics and chemistry, is how to describe interactions between atoms. And people have been doing this since the 1920s, when Leonard Jones made his first potential, the Leonard-Jones potential, which probably many of you have seen. Some of you have seen it already in high school, and certainly in first year physics or chemistry studies, you have seen the Leonard-Jones potential. Another potential which came in the 1930s was the Morse potential, which is actually better motivated physically and has still a very simple functional form. And these are returned to this, that what kind of functions have been used for potentials since then. Well, then it's also possible to do it quantum mechanically, as I already indicated. And we have also done density functional theory, molecular dynamics. But the problem with this is that they are horribly slow. For a small number of atoms, like 10 or 20 atoms, one can get them fairly fast. But already at 100 atoms, things, because they scale as the number of atoms squared, sometimes more. So it's difficult to get to large systems. And now, the main topic of my talk is these machine learning methods, which has emerged as an alternative in a way between these. And at best, they can really have the quantum accuracy, but still have the linear scaling, so you can do reasonably large systems. And to give you a brief history of interatomic potentials, for this slide, I actually have to thank our postdoc Jesper Byggmästare, who made this slide for his PhD thesis defense a few years ago. Starting in the 1920s, 100 years has almost passed since the Leonard-Jones potential. but around 1980s, things developed a lot in the analytical interatomic potential range. There was the effective medium theory and Stilling-Weber potentials. Effective medium theory was very, very valuable because it gave a quantum mechanical motivation for many-body potentials for metals, which then led to the embedded atom method and several other like two-body type binding approximation and so on potentials, which have been very successful in describing metals. And then there was torsion-like potential, which actually was also based on a second moment type binding approximation motivation with the Abel formalism, and this was also has been very good in describing both semiconductors and compounds and metals actually. So these have been quite good, but even then they have their limits. And that's why around 2000, 2005, maybe people started looking seriously into machine learning interatomic potentials. And there have been many, and new are coming regularly. And I will just mention a couple of important, the Baylor neural network potentials, which partly are some ideas from the Baylor work are used in the Gaussian approximation potentials. But these are the ones we have taken into use in our group. And now I'll describe a little bit about this, what kind of physics and chemistry goes into machine learning potentials, first generally, and then with for the gap potentials specifically. So, of course, the basic assumption of interatomic potential is you have a number of atoms, you know their coordinates, and want to know what's the potential energy of the system of atoms and the forces acting between the atoms. Almost always people have the finite interaction ranges, while the Coulomb potentials can also have infinite range with Ewald summation, but actually the ionic materials have not yet been studied very much with the machine learning metals, so it's I won't mention more about that. But then if you want to start using a machine learning potential, you need a machine learning architecture, and in principle this would be enough. I mean, because a machine learning architecture, it can be trained against any data set. So in principle, you could take a number of atom coordinates and get their energy from DFT, and then start start training a machine learning framework against this, and then take a number of any number of random atom configurations and train your machine learning framework with this. But it's fairly, if you think even a little bit about it, doing that would not be a very good idea. And there is a very simple argument for that. You could just consider two atoms, a dimer. So if you have two atoms, we know from basic physics and chemistry that if two atoms in vacuum, if the interatomic separation between them is the same and there is no external forces, then the energy of the two atoms must be the same no matter how they are oriented in space. This is comes from very basic physics considerations of invariance of translational rotation. But now if you take only the atom coordinates and start putting atoms in different coordinates and train against that one, you can't train an infinite number of separations. So it's quite possible that you would get, due to round of errors, you get the results that the two atoms would have a different energy depending on their orientation, which is obviously wrong. So that's why it's not a good idea to train against the atom coordinates directly. And that's why practically everybody who does, or everybody I know who does this, uses quantifications of the local atomic environments, which are known as descriptors, and then you would use a DFT data set to train the machine learning against against the data, which first is described by the descriptors. And these descriptors do exactly what I described, that they make sure that if a molecule is translated, just shifted in space, or rotated, or permuted, that is, atoms are changed, but the idea configurations are the same, then the descriptors are used to make sure that the energy will be the same after these operations. And this is actually where Baylor and his co-workers did quite good work, that they developed these so-called symmetry functions, which are part of the descriptors. So the first descriptor is the trivial, almost trivial one, interatomic distance. So this is exactly these two atoms, their rotation. But then you take in the bond angle, because it's of course also known that if the bond angle and bond separations are the same, the energy should be the same. But then they introduced more advanced symmetry functions, which describe the environment of the atom. This is a function of the angles, which describe the angular dependence, and this is the radial dependence. And this also has a cutoff function, which makes sure that the interaction goes to zero at a finite separation, which is good for numerical efficiency. And those of you who, if you have ever looked at the analytical potentials, will recognize that this angular dependence resembles quite a lot the torsion potential, which had a well, not an exact, but let's say a heuristic physical motivation. So they have borrowed ideas. And here you have the cutoff functions to all the three bonds in this system. But then the fourth important component, which was developed by the same people developing the gap, is the so-called smooth overlap of atomic positions, which is essentially smearing off the atom positions, like an atom wouldn't be at an exact coordinate but spread out a bit. And this may sound a bit strange, but the basic idea is that if you don't do this, if you have discrete atom positions and still you have a finite number of atoms, then you can easily get wiggly functions in the machine, final machine learning result, which again, it doesn't make physical sense. I mean, unless you have some strange magnetic or magnetic transitions or electric dipole transition, if an atom shifts only a little bit, you know that the F shift in the system energy should be a smooth function of the atom coordinate, not have any wiggles in them. These SOAP functions are essentially a way of achieving that. And then after this is done, the atom coordinates have been translated into these descriptors, which are described here. Then you can use, well, in principle, any machine learning approach to start training the system. And it is Gaussian process regression or the Gaussian approximation potentials, which we are using. This is sort of a simplified description of this. So you have the training data, and then you do Gaussian process regression to train your system against this, so that you can interpolate between all the training data, and this way the uncertainty in the training is reduced from the prior to posterior after the training. And also you see that one can also get in the Gaussian process regression, can get an estimate of the uncertainty, how uncertain it is in points which are not part of the training data sets. We have actually recently started testing this. It doesn't. It seems that this for an atomic system, this Gaussian process regression uncertainty may not actually be too useful, but we'll get back to that in some future work. So that was the basic gap, and I emphasize that these last 5 slides were not work in our group. That was all done by others, Baylor and Bartok and Shani and so on, who were developing this gap formalism. But what we did is that we looked at this, evaluated like 4 years ago several several machine learning approaches for interatomic potentials, and looked which are most promising to simulate multi-element alloys, high entropy alloys, which are our main aim. And we realized that none of them was suitable for radiation effects. And the gaps, although they are good in many ways, they're not trained against very short interatomic distances, which are very crucial to handle those KV energy collisions. Well, on the other hand, we knew from previous work in our group that with DFT approaches, you can easily get, for the repulsive part, you can easily get like 1% accuracy at the short ranges. And in principle, one could take a number of short-range interaction points and train the gap against them as well. But we thought it's sort of stupid to do that, since the almost right answer is known anyway from calculations of dimers, which are much, much faster to do than the complex solid-state systems. So what we did is we augmented the gap with a pair potential. Pair potential to this short-range data and made sure that there is a smooth overlap between them, so that we have their pair potential, but we make it to go to zero at a separation which is less than the interatomic separation in the bulk. And then in principle we add this, but then when we train the gap, of course, a gap with liquid, the DFT training set will have some short interatomic separations, which might be somewhere here. So what we do is that we calculate the pair interaction energy for those configurations, and then count it out from the energy which is the gap is trained against, then do the gap training. And that way we ensure that the gap perfectly within the data set matches these repulsive potentials, and there is no discontinuity anywhere. And here is the formalism. So after in the end, it's just an addition of a pair potential, but the crucial point is that for the gap training, you need to count out those repulsive potential energies to ensure a smooth fit. And here is just a few illustration of what happens. So this is DFT data for atom drag in a fixed lattice in certain crystal directions, and this dash curve is the original gap, and the solid points are the DFT data. So you see that the original gap is just horrible. It goes off by several orders of magnitude at worst on this repulsive part. But after we do this repulsive potential addition, we get essentially perfect agreement with the DFT data points. And I emphasize that this was not a direct fit, so it's actually training the final gap, testing the final gap against those DFT data points. And once we did all this, we were ready to start doing radiation effects in the gap potential, in metals followed with the gap potentials. So we first made a gap for tungsten, and then we could compare the results of damage production with the machine learning potentials and some classical potentials. And now I won't mention otherwise any details, except that we find also the qualitative discrepancy. The basic number of damage production was about the same, which is good news. Otherwise, we would have been doing simulations wrong for the last 30 years. But there is some that so-called type A defect, which are tungsten next to a die vacancy. This appears in the classical potentials, but not at all in the gap. And this is because DFT shows this structure to be unstable. So essentially, this shows that this is an artifact of the analytical potentials, which the gap removes. And now to maybe the most exciting new thing we have done. We have done high entropy alloys. We have studied high entropy alloys a lot. This is because it's a hot topic. There are lots of studies of high entropy alloys. If you're at all into metallurgy, I'm sure you've heard of it. It's all the metals related conferences nowadays. This is because they are promising mechanical corrosion resistant and radiation hardness properties. So using this gap formalism, we thought that we could take this basic gap and do a 5-element machine learning potential for the BCC high entropy alloy, molybdenum, niobium, tantalum, vanadium, tungsten. It turned out that doing a full gap, the training becomes too hard. There are so many configurations. If you consider all the well, you can't consider all the permutation, but the reasonable amount of permutation. But then Jesper Bygnes, the postdoc working on this, developed a so-called tab gap formalism, which is the training is done in a similar way as gap, but the final implementation uses a three-body interpolation of the three-body term, three-body descriptor, which makes it much more efficient than the full gap potential, about 2 orders of magnitude faster than the full gap potential. And then it's also possible to do actually training. But this, with this potential, one can get a really good description of this high entropy alloy in any number of configurations. So this is an example of number of random atom configurations, and here the spheres are the DFT data points, and these fit lines are the tab gap fit, and you see it looks perfect. It looks like it's just a line plotting, but it's not. This is actually, the lines are actually tests of the test of the function, even though it looks like it would just be drawing lines between the points. And overall, if one analyzes the, for instance, the error in the bulk modulus against DFT or the mixing energy, you see that the errors are very small. In the bulk modulus, the root mean square deviation is 2 GPa out of 100, so less than 1% error, and the energy deviation is a few millielectrovolts per atom. For comparison, a typical analytical potential has tens or hundreds of millielectrovolts, so it's a really remarkable improvement. So somebody raised their hands, but I guess we agreed to take questions in the end, so take it in the end. Once this is done, so we have done this, it's published, there is a reference there. But once it's done, one can really start looking at the radiation effects in this high entropy alloy. So we have, for instance, looked elemental segregation or points in the high entropy alloy, and you see that it's not random anymore. Basically, the large atoms like niobium are enriched on the inner surface of the void, but there is also a little bit of enrichment of vanadium, which is a bit surprising since vanadium is not really a large atom. So there is also some chemistry playing in here. And we have looked at vacancy migration energies, and this is actually qualitatively already a very important result, that there's a huge fluctuation in the vacancy migration energy. It's a single vacancy. Depending on which local atomic environment, the range of migration energies can be from less than 0.4 eV to about 2.5 eV. So it's almost an order of magnitude of variation in the migration energy, which is certainly a big effect. And if you look at standard diffusion theories, well, basically it shows that you can't even use standard diffusion theory because that can't handle this large variation in migration energy. So one would have to do a full atom level simulation of what's going on. Interstitials are also more complex. Now I guess I'm running out of time, so I'll go through this rather quickly, but basically you show that interstitial properties vary a lot depending on what you do. And also interstitial loops turned out to be enriched in vanadium. So the core of the loop is practically pure vanadium, which is also not a completely obvious thing. And finally, Mosab, how much time do I have? I have a few slides on silicon still, but it'll take maybe 5 more minutes.
Yeah, I think you still have time, maybe okay. 20 minutes. Yeah. So.
Okay. I just think you're leaving some time for the question. Okay, but then I'll also. I mean, I could have skipped over the silicon part, but yeah, then if somebody is interested in silicon, we also have a gap with the repulsive part for silicon, and as in the tungsten and metal part, that the original gap, there is a very good gap for silicon, but if you look at some small atom drag in some random direction, you see that the original gap does very poorly. A new gap does fairly well, although here, to be honest, we have a bit of a problem that different levels of DFT approximation give different results. So we are not sure we are exactly right here either. But we made this silicon gap potential, and we have tested it, and it seems to be very, very good. So if you look at the threshold displacement energy, which is a basic radiation effect quantity, we see that the agreement with the experiment is actually perfect within the error bars, which the classical potential Torsov-3 and Stillinger-Weber doesn't get perfect agreement, neither does DFT. Well, DFT is essentially within the error bars as well, but this is natural since the gap is trained against DFT. We could also test sputtering yields. This is a way to qualify whether this is directly high energy radiation effects against experiments. We see that the original gap does fairly poorly. The classical potentials also are about a factor of 2 below experiments. the gap, our gap potential is almost agrees with the experiments. As you see, there is some fluctuation in the experiments as well, but it could most likely, this is also related to surface roughness, which we don't know exactly what it was in the experiments, but still you see that the gap potential was clearly better than any of the previous models. And then if you look at what actually happens in cascades, so this is a potential simulated with the gap, Stillinger-Weber and Tolsov potentials. You see that the final damage is rather different. Sorry. So the Tolsov 3 potential has a fairly large complex damage remaining. This was known from before. The Stillinger-Weber and gap potential look pretty similar, but even then it seems that the final damage features in the gap potential are a bit smaller than the Stillinger-Weber potentials. If you look at this as a function of energy against the number of damage produced, again, the pure gap is not sensible at all. It turns out that the gap and the very old Stillinger-Weber potential made already in the 1980s actually give pretty similar results. But if you look at the fractional damage in clusters, it seems that there is a qualitative difference. The gap has more small clusters than either of the classical potentials. And we also figured out a way to compare average defect cluster size against experiments. This is well, the experiments are difficult to do and it's an old experiment, but if we trust this experiment, the gap potential does the best, although the Stillinger-Weber potential in terms of average cluster size is also quite close to it. And this is actually very amusing that people, I mean, the Stillinger-Weber potential was essentially the first many-body potential for silicon done in 1980. Since then, people have literally done hundreds of potentials for silicon because it's so important. Yet, quite often we find that out of all silicon potentials, the original Stillinger-Weber does better than any of the newer ones. But we found an interesting feature as well. So the gap potential found a new defect configuration, which is one vacancy surrounded by 3 interstitial. So the balance is a di-interstitial. There are 2 extra atoms. This configuration is interesting in that every atom has 4 bonds. They are in a peculiar configuration, but they still have 4 bonds, which of course is the equilibrium number of bonds in silicon. So it turns out that this is quite stable. And this was a defect type which we didn't find that anybody had described in detail earlier. It's similar to the IV pair, but it's really a di-interstitial, so it's not the same thing as the IV pair, although there are some qualitative similarities between them. And this actually brings me to the end of the talk. If anybody is interested in a PhD position, we have 2 PhD positions which soon will officially open, but we already know we have the funding. So if you're interested, just email me and I can tell about it. They are both, one relates to silicon and the other relates mainly to metals, so fusion reactors modeling. Both are fully paid 4-year PhD student positions. I imagine you probably are our PhD student, but maybe you know some younger friend who might be interested, so feel free to inform about it. And then also we have published quite a lot. Here is a summary of all the papers we have published on machine learning potentials. So we started publishing this topic 3 years ago, and since then we've got a number of papers already on this, and several more are in the pipeline. So this is really an active topic of research right now. We have finished potentials for copper and nickel as well, but haven't just written them up yet. So to summarize, first of all, I hope I convinced you that radiation effects are important and interesting to study. Then regarding the main part of the talk, so you see that for machine learning potentials, they on the one hand, they seem to confirm what we knew, that is the main results are the same as for the analytical potential, which is quite good. Otherwise, I could have, I personally would have about 500 of my publications would have been useless. So I'll be quite happy to see this. But then you do see new features which were not obvious from the analytical potentials related to defect cluster sizes, new defect configurations, and so on. So they really do give an advantage. And also because there are systematic training framework, they are sort of easier to make than the analytical potentials, because making analytical potentials has always been fitting them has always been a little bit of an art, and which can give lots of gray here. So it seems that there really is an advantage of doing the machine learning potentials if you know what you're doing.